we now come to the conclusion of this course, line commutated and PWM rectifiers, and in today's lecture we will talk primarily we will try to summarize what we have learned in this course, right? So let us again look at the course structure and the content, and you can see we have divided the course basically into 4 modules. Okay, overall we have what we have learned in the course are different types of power converters, okay, and circuit topology, operation and control. Okay, these are the things primarily we have covered in this course, and we have divided the course into 4 main modules. In module 1 we had this diode and thyristor rectifiers, basically line commutated converters, okay, and in which we also dealt with the multipulse rectifiers to improve the THD of the input current. Next we had the module B, which was exclusively on AC-DC voltage source converters and their operation, their modeling and the control of this, okay, which was covered. Then we went into module C, which was primarily we were focusing on single phase AC-DC converters. This includes the this includes the Totem-pole PFC converter, boost PFC converter and flyback AC-DC converters. Okay, so these were the single phase converters that we touched upon. And then we went to module D, which was basically on rectifiers for applications like EV and battery charging, in which we talked about 3-level NPC and VNR rectifier, and also we touched briefly about the battery energy storage system, large scale battery storage systems, BMS and EV charging. Okay, so this was the overall content of this course, and we will now go through all the 4 modules one by one, but briefly touching upon the salient features of these modules. So we first started with in module A we started with the diode bridge rectifier, very well known, where we said that suppose you have a very stiff current source at the output side, then we have the diodes which will be conducting in a particular sequence, okay, so depending on which diode gets forward biased at any point of time. And although this is very advantageous because the diodes will commutate on their own, but from the input point of view, this current here, okay, this current will become a quasi square wave, okay, very rich in harmonics. Okay, this current here will become very rich in harmonics, and which will be unacceptable for the grid supply. Okay, the supply system here, okay, will say that you are drawing too much of harmonic current. Okay, so one way to understand the effect is to do a Fourier analysis of this input current. The input current is a quasi square wave, and when we do the Fourier analysis, which is shown by this formula here, we found that all the harmonics are at these frequencies. Okay, 6n plus minus harmonics are present. Okay, and so we suppose the 5th harmonic is 20%, 7th harmonic is 14%, like that. So and the measurement of the harmonics is done by this thing called as the total harmonic distortion, or THD, which is defined by this expression here. Okay, which is basically the contribution of all the harmonics divided by the fundamental. Okay, so we have certain restrictions from the grid standards like IEEE 519 standard, where we say that the THD of input current should be less than 5% for any converter, right? So this feature or this phenomenon of diode bridge rectifier conducting for a constant current load is also equally applicable for a thyristor bridge rectifier. Okay, thyristor bridge rectifiers are not so popular nowadays because we are no longer using DC machines like before. But still, thyristor bridge rectifiers are used in HVDC transmission and also in some special applications which we have seen in the course, like an electrolyzer. Okay, so in case of thyristor bridge rectifier also, this same phenomenon of a quasi-square current waveform input at this will be noticed. Okay, one thing that we must be careful is that how we define alpha in a three-phase rectifier. One must keep in mind alpha starts from the point, this point here. Okay, this is alpha equal to 0 degree, and then the alpha moves. It is the point where VAB voltage becomes the highest. Okay, this is very important to note. So as we see here, when you change the value of alpha, what happens? So as you can see here in this diagram, the source current, okay, is a quasi-square wave, but it starts to shift. Okay, it starts to shift with respect to the voltage. The current starts to shift as we change the value of alpha. Okay, and therefore the total power factor, which is the product of DPF and DF, distortion factor and displacement power factor, right? So power factor then becomes equal to cos alpha into 0.955. 0.955 is the distortion factor for the this quasi-square wave current. Okay, so we find that the power factor of the input current gets worse as we increase the firing angle. Okay, so which means that the power factor is getting poorer, we are going to draw more and more reactive power, and this is one of the biggest drawbacks of the thyristor rectifier, is that not only is the distortion factor not equal to 1, okay, so we are basically drawing a highly non-sinusoidal current along with a huge reactive power. Okay, so both these phenomena happen with thyristor rectifiers, that highly non-sinusoidal current is drawn along with a high value of reactive power. Okay, so this happens here. So what is the first solution that we saw? And the first solution was to use a star delta 12 pulse transformer. Okay, and it will reduce substantially the harmonics in the input current. In fact, what will happen now is that those 5th, 7th and then 17, 19, these harmonics actually disappear. Okay, so in general 12n plus minus 1 harmonics are present. Okay, so here you have this one primary star and two secondaries, one in star and one in delta. Remember that there is a √3 ratio between the turns ratio of the primary and the secondary. The output voltage definitely improves because now we have 12 pulses, but what happens at the input side is something which is advantageous to our study, and that is the input current waveform. This current here becomes closer to sine wave, and this we have derived in the course, how we went or how we got this kind of a current by adding the two currents IA dash and IA and reflecting it into the primary side. So when you do the Fourier analysis of that current, okay, Fourier analysis can be done, and we did it by splitting it into 3 parts, right? And then we found out how much is the Fourier analysis, and this actually led to the conclusion that only the 12n plus minus 1 harmonics are present in the input current. So a star delta 12 pulse transformer actually improves the harmonic substantially. Okay, but it may not be enough. number one. Number two is that the problem is we are going to use a huge size of transformer. This is all 50 hertz transformer, okay, and the size will be enormous, okay, this one primary to two secondaries and all. So there are better solutions rather than this. And also, if we use diode bridge rectifiers, the power flow is unidirectional, okay, and we also want to control the power in a bidirectional way, and we want to control much more accurately, okay, much more precisely and easily, okay, for which we have to move into controlled rectifiers, okay, controlled rectifiers, fully controlled rectifiers, like with IGBTs or MOSFETs. And there what we see is basically the voltage source converters, okay. So this is the voltage source converter, and here is the grid, and suppose we want to rectify or inject current, okay. So this was part of module B. So we went into module B and we said that we want to precisely control the P and Q, okay, which is exchanged with the grid, okay. So this is like bidirectional. If the VSC is fed from a battery, for example, then this is like a bidirectional in nature, okay, the P and Q. So you can deliver to the grid or you can absorb from the grid, okay. So the grid connected VSC with a L filter is shown, and the control and other aspects of this voltage source converter is very similar to a motor drive also, okay. So what we learned here can be also applied to motor drives, okay. So for example, here this VSC is basically made up of a two-level converter, okay. You can see here with IGBTs, but you can also make it with MOSFET. Now what happens here is, based on the control and the way we modulate the voltage source converter, basically this VSC here becomes like a three controllable voltage sources, which actually is interacting with the grid voltages, okay. So these three controllable voltage sources, the magnitude, angle and the frequency of this is adjusted by one of the PWM methods. So we studied two PWM methods, one is sine PWM and the other is space vector PWM, okay. So with this, basically you are going to control the voltage at the output. And what is the idea behind controlling this voltage? Okay, so first we see that, okay, when you do this control, or when you switch the VSC in that way, what you see here is that the instantaneous equation can be written like this, but at sinusoidal steady state we have this equation coming, okay, which is basically very similar in operation with the synchronous machine connected to the infinite bus bar. So in a synchronous machine we also had the excitation EMF E, and then the synchronous reactance X, and then the infinite bus bar, the grid voltage. Here also we have the voltage produced by the inverter, which is acting like an E, and then you have an X, which is the basically the filter's reactance, and of course there is an R of the filter, and then you have the grid, okay. So it is very similar in operation with a synchronous machine. In fact, we saw that a 4-quadrant operation of this voltage source converter is also possible. Yeah, but what is important is that how do we control the voltage from the voltage source converter? And because this voltage source converter, we would like to control for active and reactive power, okay. So this is the phasor diagram which we have seen earlier, and where what we are doing here is, suppose the current is here and we want to keep the same active power, but we want to change the reactive power, okay. So IAG1 has to be moved to IAG2, right? Because this has the same P, okay, but the Q here is changing. Okay, this is Q1 and this is Q2, but P remains same, okay, which we are exchanging with the grid, right? So for that to happen, the converter's voltage must be changed from VAN1 to VAN2. So if we can draw these two steady state phasor diagrams, we will say that if I move VAN1 phasor to VAN2 phasor, then we have been able to achieve this constant active power. Okay. Therefore the grid voltage remains the same here and this phasor can be drawn. However, now the other case is also possible, which is known as the constant reactive power. Okay, suppose you want to keep the reactive power same, but you want to change the active power, then you can also see that you can move your phasor, you can move the current which you are drawing from the grid by keeping the Q to be same. Okay, but now these are two things, P1 and P2. Okay, two active powers. Okay, so we took an example of a PV source whose output is changing based on the solar radiation, but the reactive power which it is supplying is same. Okay, now this is an important statement. How fast the operating point moves from one steady state to another is dependent on the controller's performance, right? So how fast VAN1 moves to VAN2 is what the controller decides. And in order to design the controller, we must have a very good model of the plant. Okay, and then only we will be able to design the closed loop control system. So we first have to develop the model of the converter, and then we have to plot that model, and we have to do a Bode plot of what we did was we plotted the plant model along with the compensator or the PI compensator, and we can actually design the whole closed loop system. We have done this and we have extensively shown one simulation also in the course. Okay, how to manipulate the Bode plot, how to change the bandwidth, how to rise, fall, like that. But before that, actually also we did one more thing, was that we said that sine PWM, with respect to sine PWM, there exists another switching technique which is called the space vector PWM, SVPWM. And SVPWM is a switching technique which is based on the space vector diagram, and this is the space vector diagram with the different switching states. Okay, and by switching on these vectors you can actually realize the reference vector, or that VAN, VBN, VCN. This can be realized by switching on these vectors. And in space vector PWM you have the switch for T1 period, T2 period and T0 period, and in space vector PWM we have this condition. Okay, and these things can be known by mathematics, or okay, this can be done through mathematical analysis, or it can be done graphically, and we had shown a easy technique by which we can do this graphically by using half minus half of Vmax plus Vmin, this formula we used. Okay, by which when you add this common mode voltage to the three phases, you actually get space vector PWM. You do not have to do any sector calculation, timing calculation, nothing. Okay, so you add this common mode voltage, and this common mode voltage is typically given by this black colored waveform here. This is the common mode voltage which is added. Okay, here, and when you add that common mode voltage, what you get is this waveform here, okay, which this sine wave now gets changed to something like this, and with this what happens is you get 15% extra voltage. Okay, you get 15% extra voltage, and that is what one of the advantages of space vector PWM. Okay, so this is what we studied, and then we went into the modeling of the plant or the voltage source converter, for which we said we need two transformations. Okay, one is Clark transformation and another is Parkes transformation. And in Clark transformation, basically we have this rotating space vector. This space vector may be the grid voltage space vector. It is rotating, and we are observing as a stationary observer, okay, on the alpha axis. So here we have this alpha axis here and the beta axis here. Okay, these are stationary, and we can see the this one. On the other hand, if you see the Parkes transformation, what happens is the observer is actually rotating with the d axis. Okay, so observe the rotating space vector from two moving axes, so the observer is also moving, and that's why what happens here is the d and vd and vq, for example, will become constant values. Okay, so this is a synchronously rotating reference frame, right? So with this Clark and Parkes transformation, we actually come to the overall control system, in which you can see here these three-phase quantities. After doing Clark transformation, this becomes the two-phase quantities, and then after doing the Parkes transformation, we get to DC quantities here. And with these DC quantities, we actually have we can design the tuning, or we can design or tune the controller parameters. Okay, so the model is at the DC, okay, or with a small variation over the DC. So once we get the outputs from this controller, then we do the inverse Parkes transformation, because we have to ultimately go to the AC. So we do inverse Parkes and then inverse Clark, and we get VA star, VB star and VC star. Okay, this way, and then we put the switching logic here, and we get the go to the VSC. Okay, so yeah, so in order to design particularly the controller tuners, what we said is we have to get the space vector equations in the DQ frame, and these are the equations. Okay, there are two equations, one for the D axis, one for the Q axis, and we found out that this is the equation, and we can write it in the D and the Q domain like this. Okay, then after that we said that we will align the grid voltage space vector with the reference, okay, rotating reference frame. The rotating reference frame is aligned with the grid voltage space vector, so that V grid Q becomes 0 and V grid D becomes equal to the space vector magnitude itself. And then when you substitute in the previous equation, then you get a modified equation from this, which after doing a small signal modeling and doing a perturbation and small signal, we get V con D, and so this kind of a equation comes, whose diagrammatic representation is this this diagram here. Okay, where we see that there are cross coupling terms, okay, between the D and the Q axis, and these cross coupling terms are going to slow down the controller performance, okay, and it is not desirable. So what we do here, so this is the model of the plant. The plant itself has this cross coupling term. So what we do is that inside the controller, which is shown here, okay, this is inside the inside the controller, we actually add feed forward terms so as to cancel the effect of the cross coupling term. Okay, so inside the controller means here inside the controller, this is this series of these lines of codes are running, and in this way we will be able to make this whole control system work. Okay, so with this one we actually did many things in this one we have not included in these slides. Here we did the closed loop control, inside the closed loop control we did PI tuning, and we also did a Bode plot analysis, okay, where we actually could change the loop gain by changing the Kp Ki values. We could change the bandwidth, we could change the steady state error, I mean the 0 dB crossover frequency. So we did all these things, and then we also did a detailed simulation in MATLAB. Okay, we showed that which was we had run that as a like a running simulation, stopped at different points and saw that in spite of the fact that the voltage is the grid voltage, if there is a sag or something like that, then also the same P star and Q star can be fed into the grid with a very good current which is drawn from the grid with that very less THD. Okay, so this is something which is possible. Remember, in that closed loop control, what we are doing is we are asking the converter to see, this is like IGD star and IGQ star, which means we are putting a P star and a Q star. Okay, so a three-phase voltage source converter, okay, when it is in the grid following mode, okay, so it follows the grid, we basically set the P star and Q star. This needs to be exchanged with the voltage source with the grid. Okay, remember at the end of the course we talked about grid forming converter, where we do not use P star and Q star. In grid forming converter we used V star and omega star. So this is something which is coming up, and a battery energy storage system is going to play a very important role in the grid forming converter, because it will itself form the grid, okay, like a microgrid inside a microgrid or something like that, and so it will act like a synchronous machine or a virtual synchronous machine. So a grid forming converter, which is the control is different, although the topology, the structure, everything remains the same, but the control is different. Okay, so it will act as if it is like a synchronous machine, another synchronous machine fed from the battery storage system. Anyway, so for the initial part of this piece, this one, the at this point here in module B, we did not talk about grid forming converter. In module B, we were always saying that we are using a grid following converter, okay, where we set P star and Q star. Right, after this we moved into module C, okay, where we were talking about several single phase PFC circuits, okay, like PFC boost converter, flyback AC-DC converter, totem-pole bridgeless PFC converter, like that. Okay, so if you see here, the PFC circuit with DBR and boost converter is shown. These are typically used in single phase, generally less than kilowatt, 1 kilowatt of power generally, but many of them, like the Totem-pole PFC, can be easily scaled to 3 kilowatt or even more, and these are very important upcoming applications for single phase charging of EVs. Okay, these are very important converters or rectifiers, I should say, and so we have dealt this in details. Okay, for example, the first one we took was this PFC boost rectifier. Okay, and here you can see it has a DBR at the front, and then you have a boost converter at the back, but this must be closed, this must be working, the converter must be working with a closed loop control. Okay, and for example, the voltage here is something like this voltage here. Okay, so basically here you can see some of the waveforms here. So this important is this inductor current. Okay, the inductor current waveform, this current here. Okay, this current is a rectified sine wave, right, with a high switching frequency ripple. Okay, so when you draw the when you take the IAC, what you see is this current only, but now it will be something like this. Okay, and in many cases this THD may be acceptable. Okay, there is also, apart from THD, one important factor that must be kept in mind is the total EMI that this the EMI that is being radiated or conducted by this converter, and so we may need some additional EMI filtering at the input of the PFC boost converter to take care of that high switching frequency which is on the, because coming of the switching action of the MOSFET here. Okay, so if you zoom in on this portion, if you zoom in, okay, this is the zoomed portion, you will see that the inductor current is rising and falling like this. Okay, however, the instantaneous value of the inductor current, okay, although it is changing here, the instantaneous value is continuously changing. Okay, so it rises from 0 to the maximum value I max and then again reduces to 0 here. Okay, so this is the this is how the PFC boost converter actually maintains PFC. Okay, of course this is unity power factor, because we will force this current to follow the voltage. Okay, the voltage is here, so it will force the current to follow the voltage, right? So this is how the PFC boost converter works. But it is also important to note that these boost converters are often designed to run at the boundary of CCM and DCM, and this is the critical conduction mode, CRCM mode. Okay, so here what happens, the reason why we go into DCM mode or CRC, critical conduction mode, is because at these values the size of the inductors can be reduced. Okay, because we allow more ripple. Okay, we allow more ripple as compared to the CCM mode. So higher is the ripple, you can L is inversely proportional to the ripple content of the current. So if you increase the ripple, if you allow more ripple to come, then you will decrease the value of L. And in CRCM, the peak to peak ripple is double the average value. So this is the average value and this is the peak, okay, of the current, right? So this happens in a boost converter. We have also taken an example in the course, in the lectures, where we said how much will be the design of the inductor. We took two values of the inductor and saw how much it is changing. Okay, so this was also part of the lecture. The next part of the lecture in module C was the flyback converter, flyback AC-DC converter. At first we studied flyback DC-DC converter. Okay, this is the circuit topology that we used, and the reason was to understand the DC-DC converter first, because in many undergraduate courses flyback DC-DC converter is not taught as a first course, in the first course. So we first studied flyback DC-DC converter, and we found out that here is a transformer and there is a switch here, but this transformer is not working like a transformer. Okay, which means that the current does not flow simultaneously in both the primary and the secondary windings. But rather what happens here is the transformer behaves like an inductor. It stores energy during some part of the cycle and it delivers that energy some other part of the cycle. So it is more like behaving like an inductor. And these are some of the kind of like steady state waveforms. Okay, and these are some of the equations. which we have already covered in the course, right? So in the AC-DC DCM flyback converter, so generally these AC-DC flyback converters operate at DCM. So here what we do is we connect a diode bridge rectifier, and then the flyback converter comes here. Okay, you can see this one, but it usually acts in DCM. Okay, so this is the current here, right? And the current you can see is having 0 period in between. So we analyzed this type of converter, and we found out that ultimately this current, or rather not this current, ultimately this current here must be at unity power factor and sinusoidal. Okay, because it has to be following the grid codes. Okay, so therefore the overall, this looking into this direction, the emulated resistance, okay, will be like a resistive load to the circuit. Okay, so RE, we use this RE several times, is the emulated resistance. Okay, the resistance which appears, okay, for this one. So yeah, so the ratio of flyback converters average input voltage and average impedance should be constant. Okay, so we use this several times. Okay, next, from the flyback converter, or from the AC-DC flyback converter, we moved into Totem-pole PFC converter. Okay, it's a bridgeless PFC converter. It is more advanced on this one, because here the power rating can go very high, and we did some circuit manipulations moving the diode bridge. One of the things that you see is now we have moved the inductor back from the DC side into the AC side. Okay, earlier this inductor was on the DC side, now we moved it back into the AC side, and what we did here is that we used 2 high frequency switches. These are 2 high frequency switches, and we used 2 low frequency diodes. Okay, here. Okay, and how or why did we use like this, we have discussed in the course. Okay, so S1 and S2 can operate like 50 kilohertz, and D1 and D2 will be operating at the grid frequency, right? And so this converter has a very good potential for many of the future applications, right? And if you compare this Totem-pole PFC with respect to the PFC boost converter, then you find that in boost PFC we have low frequency diode, four low frequency diodes, whereas in Totem-pole we have 2 low frequency diodes, right? On the other hand, in the conventional bridge we have one high frequency, so this is that high frequency diode, and we do not have any high frequency diode in the Totem-pole. And in the boost PFC we have 1 high frequency switch, this one, and here we have 2 high frequency switches like this here. Okay, so overall we find that because there is no high frequency diode and the number of low frequency diodes are less. Okay, remember this low frequency diodes are switching at 50 Hertz only, right? So what happens is overall the Totem-pole bridgeless PFC has a higher efficiency. Typically we are seeing nowadays efficiencies getting reported greater than 98%, whereas this one is typically less than 95%. With silicon carbide, these are the values which are coming up nowadays. Of course, betterment is going on, happening all the time. Okay, now then we moved into module D. Okay, in module D what we studied were some 3-phase converters, right? One of them with the 3-phase NPC, which is used for high power applications. Okay, it's acting as a rectifier. So here actually is the grid. We have not talked about the grid here. So here is the grid here. Okay, and it helps in making the input current THD lower and the filter size smaller. Okay, so this was one of the advantages of a 3-level NPC, okay, neutral point clamp, and we also saw the space vector diagram for the 3-level NPC, which has actually 27 space vectors. In this there are 2 hexagons and 27 space vectors. Okay, one important offshoot for this 3-level NPC, from this 3-level NPC, is the Vienna rectifier. Okay, that also we studied. In the Vienna rectifier, what happened was that there are 2 forms of Vienna rectifier, both are identical, but if you look from this to this side, sometimes you are charging through this diode, and sometimes in A phase you are going through this. So in the positive half of the AC cycle, this diode is conducting, and this is the path of the current, and in the negative half of the AC cycle, for example, you can have this one. Okay, means one half and the other half. In one half you are using the red line, and in the in one half itself you are using the red and the violet colored one to charge and discharge this inductor. Okay, but in the other half of the AC cycle, what you will do is, in the other half of the AC cycle, you will use this diode. Okay, right, this diode and this switch again once more. Okay, so basically these 2 diodes are used alternatively, in one in positive half cycle and one in negative half cycle, for charge discharging of this inductor. Okay, and this is a 4-quadrant switch which will be used in both the half cycles, right? And so basically what we see here is this is a rectifier which uses these 2 diodes alternatively, and through these 4-quadrant switches it can actually have a very nice performance. And Vienna rectifiers, again, for 3-phase applications, it has been reported like more than 98% efficiency, right? But remember, Vienna rectifier is a boost converter. Okay, it is a 3-phase boost converter, right? Because looking from this side, the DC link is more than the DC link is more than peak of AC. Okay, so this side is AC and this side is the DC. So basically looking from this side, it is a boost converter. Okay, and so this inductor is here, and it is as if like once it is, this diode is conducting, and once this switch is conducting. Okay, and so the charge discharge is happening. And it is a 3-phase 3-level unidirectional. It is unidirectional. Energy is flowing only this way. Okay, on the other hand, if you look it carefully, which we have discussed in the course, the T-type, this is the T-type NPC, and the T-type NPC is identical to the Vienna rectifier. Okay, why? Because you have, if you remove this IGBT here, and then it becomes, and this is a 4-quadrant switch. Okay, so then the T-type NPC is identical to the Vienna rectifier. Of course, we have changed the IGBT to MOSFETs, right? So basically, but then you can work like a, so you can look from left to right, but you can also look from right to left and operate it as a voltage source converter. Okay, you can do that if you look from the right to left. Okay, so this is possible in this the feature. Okay, yeah, this is where the charging and discharging has been shown here. Then the circuit gets completed to the other phase, the 3-phase VSC. This we have discussed in details. And then we moved into several types of EV chargers. We said the onboard charger, integrated onboard charger, wireless charging, and off-board DC charging. We briefly touched upon all these, and different types of topologies are used in onboard chargings. For the front end part, AC-DC, we have boost PFC or Totem-pole boost PFC, Totem-pole boost PFC rectifier. This is possible. or we have the at the front end AC-DC stage, we can have a 2-level voltage source converter, VNR rectifier, or the T-type rectifiers. Okay. During this point, we also briefly touched upon this dual active bridge converter, because this is one of the important DC-DC converters which we can use in the overall as part of the onboard charging. Okay. It can be used for several kilowatt to tens of kilowatt, even 50 to 100 kilowatts of DAB are coming up. We touched upon this dual active bridge converter, and we saw that it is basically two edge bridges. Okay, left hand and right hand edge bridges working together, in which there is an inductor in between. Again, you can think of that this voltage here is a controllable voltages, quasi square wave, and this voltage here is again a controllable voltage, quasi square wave. Okay, by manipulating these two voltages, you can and control the power flow along this inductor. This is the basic idea of a dual active bridge converter, and these are some of the waveforms which we have discussed, and the current is like this in SPS mode. Okay, but other modulation techniques exist like EPS and TPS, by which you can reshape or modify the inductor current. Why will you do that? Because if you do like that, then you can change the efficiency, the losses of the inductor. You can change also that soft switching part of the inductor current. Very important, soft switching of DAB. We have touched upon it, and that increases the efficiency of DAB. And in the last few weeks, what we studied, one thing that we studied was the battery energy storage system, which has several functions. Like this is the battery storage, which actually helps these renewable energy sources by having a backup power or a spinning reserve. Okay, it supports it, but it also has this power quality improvement or frequency support in microgrids. So we said this can be a grid forming converter. It can behave like a synchronous machine, as a virtual synchronous machine, not as physical synchronous machine. It can add to the inertia of the system, right? So these battery packs are going to play a very important role in the future grid. Okay, so studying the BESS as a part of the rectifier system is also important. Okay, and there are several structures of these BESS, and we have these battery packs here and DC-DC and DC-AC converters. We also saw this kind of ISOP and IPOS connections. Okay, yeah, so input series, output parallel, output series, this kind. So they can actually share the input voltage. The input voltage is very high, output voltage is low, then we go for ISOP connection, input series and output parallel, so the current will increase like that. Okay, and we also touched upon electrolyzers as one application of a very high current rectifier. Here electrolyzer can touch about hundreds or thousands of amperes. Okay, and the power and electrolyzers, why did we study this one? Because we see that hydrogen production for many applications, in particular for the transport sector like a fuel cell, this hydrogen production is going to play a very, very important role in future. Okay, so this is an alternative to battery energy systems. So electrolyzers are also, large scale electrolyzers are being developed throughout the world. Okay, and this is one topology of the thyristor. We most of the time we use thyristors to handle that high amount of thousands of amperes of current. We generally go with these 12 pulse thyristor rectifiers. Okay, so so with this we come to the conclusion and end of this course, and thank you for being part of this whole journey. And yeah, so we also, as an instructor also, I learned many things during the course, because I believe that the best way to learn is to teach. So you have to do the opposite thing. If you don't know anything, you do the opposite thing, and then you will find that actually you have the knowledge inside, you didn't know that the knowledge was inside, so it will come out automatically. So with this we conclude the course, and I hope you have enjoyed and learned something from this course. Thank you.